So for our last video, we're going to put it all together. To be able to put it all together, we really have to be able to recognize very quickly whether something is a strong base and a strong nucleophile, or whether it is a weak base and a weak nucleophile. And we have to be able to identify all of that because it's going to be the most important thing when determining what kind of reaction is going to happen. Is it going to be an Sn1, an Sn2, an E1, an E2? What kind of reactions are we going to have, and what is the major product going to be? So this is the main concept of this chapter that you're going to be expected to do. You're going to be given a substrate, you're going to be giving a nucleophile / base, and you have to determine what kind of reaction it's going to do. In order to do that, we've already been able to identify substrates. We know that substrates are primary, or secondary, or tertiary. So that's the first thing that we need to know. The second thing we need to know is whether something is identified as a strong base or a strong nucleophile. So what does that look like? So if we divide it into 4 different corners, we have certain things that are really strong bases but weak nucleophiles. Again, what does that mean? That means that they have a tendency to steal hydrogens, but they do not attack the alpha site. Do not attack alpha site. So what are examples of something that are strong bases but weak nucleophiles? And we have several. Some that we've already seen, NaH, and we explained that the reason why it is a strong base is because it wants to take a hydrogen. And the reason why it's not a very good nucleophile is because it's not polarizable. If you don't understand that concept, please go back and watch the previous video that explains that the more electrons you have, the more polarizable you are, the better nucleophile you are. So other things that are strong bases and poor nucleophiles, they can't attack the alpha site. It must be because they're too big. So you can most often recognize, even if you've never seen one before, you should be able to recognize something that is a strong base. It's going to have a negative charge. And a weak nucleophile means it's too large to attack the alpha site. So typical kind of things that are listed in your book are DBN, DBU, and I don't need you to know what these look like. I just need you to recognize that this B is going to give you an indication that it is a very strong base. That's not actually what the B stands for, but for our purposes, let's go ahead and assume that it is. So it is a base, and it's too large to actually act as a nucleophile. Other examples that I gave you in my previous video is something that is very, very sterically hindered. Another example was diisopropylamine. Again, all of these are negatively charged. They're very strong bases, but they're too large to be good nucleophiles. There is one that is kind of borderline. It's the go-to example, but it actually isn't as big as I've led you to believe. So I'm going to put it in orange, and I'm going to put it in this corner because it is somewhat a borderline because it has 3 methyl groups, but unlike the others that are even much, much larger, it's large, but it's not out of this world large. So it would be great if everything fit perfectly into one of these 4 quadrants, but you will find many examples that don't fit easily into these 4 quadrants. What do you do when you have something that doesn't fit easily into these 4 quadrants? You have to go and you have to find more information. And you either have to search in the internet or search within your textbook to find out where it actually fits. Some of them kind of fit somewhere in between, and the only way that we can really figure it out is if we actually do the experimentation. For the most part, I know that I am not going to ask you things that are borderline unless I've specifically told you which quadrant it actually fits in. And even if we do come across multiple choice, which I don't make, and they do ask something that's borderline, if it's a questionable question, I will actually throw it out. Because I'm not interested in you knowing every single thing. I want you to understand the trend. And the trend is that strong bases have negative charges and are too large, this being an exception, to be able to be good nucleophiles. So these things are strong bases, but very weak nucleophiles. So what are things that are strong bases, but also strong nucleophiles? Well, these are things that have negative charges, because that's what makes it negative, makes it strong, but they also are very streamlined, so they can attack the alpha site. So examples of things like this would be an OH, And remember that we can call it an OH, but this OH really is equivalent to a whole lot of different kinds of hydroxides, right? It can be sodium hydroxide, it could be lithium hydroxide, it could be potassium hydroxide, it could be any version of those, but all of them are exactly the same thing. They're a hydroxide when they're actually in solution. What other kinds of things? Well, really any oxygen with a negative charge. So ONE, OET, any of oxygens with negative charges that are not very sterically hindered are going to be strong bases and strong nucleophiles. Once they start getting somewhere in between, then they're strong bases and not as good of a nucleophile because they're so sterically hindered. Other kinds of things that are strong bases but are still streamlined, well, carbon that is triply bonded with a negative charge, it's going to be a strong base, it's going to be a strong nucleophile. Things that we're going to begin to see in these later chapters are things that look like this, but what does this really mean? We have to remember that the lithium is just a positive charge. So what that lithium is telling us is really that we have a negative charge on a carbon, and that's going to be a very, very strong base because carbon does not like being negative. It's also very streamlined because it's in a straight line, so it's also going to be a very good nucleophile. And finally, things that have nitrogens with a negative charge. So nitrogen with a negative charge, and again, it might or might not show the negative charge. It could be a sodium, it could be a lithium, it could be a potassium that's in front of this group, but nitrogens with a negative charge, so long as your R group is not very sterically hindered. The more sterically hindered your R group is, the less chances that it's going to be a strong nucleophile. So it becomes a weak nucleophile when it has a lot of steric hindrance on it. But as long as there isn't a lot of steric hindrance on it, it is both a strong nucleophile and a strong base. So let's go through the third section. The third section is specifically looking at things that are strong nucleophiles but are weak bases. So we talked about this being the case of different kinds of atoms that are polarizable. So atoms that are very large and have a negative charge are going to be very good nucleophiles, even though they're not very good bases, because they can stabilize that negative charge. And the classic examples are all of the halogens. So this right here, and this right here, and this right here are much better nucleophiles than they are bases. So when you go back and you look at that first problem set that you did that only discussed substitution reactions, we hadn't really talked about polarizability yet. And so therefore, we might have concluded that some of the substrates were more likely to do one type of reaction than another because we didn't think that they were very good nucleophiles, because we didn't understand the concept of polarizability yet. It wasn't until later in the chapter that we were able to understand that things that have a lot of electrons, even though they're very stable with that negative charge, are capable of being polarized so that they can act as nucleophiles. So therefore, as long as what they are replacing is more stable with the negative charge, they will do that replacing. There are better nucleophiles than they are bases, and they do not remove protons. Other things that also have a tendency to do this are larger compounds. So sulfur is much larger than OH, so it tends to be a much better nucleophile than it is a base. And finally, even though they're neutral, and we tend to think things that are neutral as being weak, because they're neutral and also are in the lower row, the third period of the periodic chart, they have an excess of electrons that they can use to become very good nucleophiles. So sulfur, even though it's neutral, is a very strong nucleophile. So other examples of that are RSH, again with two low pairs of electrons, so long as your R is not very large. If your R group is sterically hindered, you're now going to become a weak nucleophile because you can't attack the alpha site. So it's all common sense, and even though you might run across something that has never actually shown up on this chart before, you still should be able to figure out whether it is strong or not. One of the things that I would like you to remember, and it is kind of borderline, so we're going to put it in quotes. It turns out that there's one that's difficult to understand, and that is your nitrile. Your nitrile with a negative charge, you need to go and specifically look up. There's a passage in the textbook that tells you, look, this guy's borderline. He's a pretty darn good nucleophile, but he's not exactly a weak base. We're going to put him in this category as far as my class is concerned, but he doesn't fit very well into any of the categories. However, I tend to think that nitriles, and this is my personal belief, not anybody else's, that nitriles tend to do more substitution reactions than they do elimination reactions because they are better nucleophiles. And that has, again, it has something to do with the triple bond that's holding on the carbon in the nitrogen. And I'll leave it at that. But it is a questionable thing, but for our class, we're going to put that under the strong nucleophile but weak base category. Finally, we'll have a category that deals with nothing but weak bases and weak nucleophiles. What kind of things are weak bases and weak nucleophiles? 99% of the time, these are solvents. Now, they have to have lone pairs of electrons. Because if they don't have lone pairs of electrons, they are neither a base nor a nucleophile. So if you're looking at some of the aprotic solvents, it's going to be very difficult to define them as a nucleophile or a base because they do neither, okay? So in all of these cases, what we're talking about when we're talking about a solvent is we're talking about a lone pair of electrons that actually can take a proton or can act nucleophilically and attack an alpha site. They very rarely do because they don't have a lot of motivation to do it. So things that fit into this category are protic solvents. So classic examples are water, are ethanol, maybe even isopropanol. Any kind of neutral lone pairs of electrons on an oxygen are the most common ones. Occasionally, you will find something that has a nitrogen. Nitrogens tend to be more nucleophilic than oxygen because they're less stable with their negative charge, but this nitrogen is very sterically hindered. So again, this would be considered a weak base and a weak nucleophile. It's too large to be a nucleophile, and it's not negative, so it's not strong enough to be considered a strong base to be able to pull off a proton, but it's more likely to do so than the oxygens. So most of the time, our weak bases and our weak bases are oxygens with a lone pair of electrons. So now that we're able to identify all of these things into these 4 different quadrants, and I highly recommend that you make flashcards or make little 3x5 cards that have all of these examples so that you can at least look at them and revisit them over and over again until you cement them in your mind. Are there going to be things that are not in this area? Yes. Should you be able to put them in the correct quadrant if you come across them? Yes. You're looking for something that is negatively charged here. You're looking for something streamlined that goes over here. You're looking for something bulky that goes over here. You're looking for something that is polarizable, extra electrons. Notice that this is the category that has the most variation. It has things that have negative charge, and it also has things that are neutral. Where in the others, it's pretty clear-cut that everything around here is negative, everything over here is negative. This one has both, and everything over here is neutral. So by looking at the charge, it might also help you to determine what quadrant it goes into. Now that you've determined how to figure out whether something is a strong nucleophile or a weak nucleophile, and a strong base versus a weak base, now it's time to put it all together. In order to be able to put it all together, you have to rely on a chart that I created years ago and Dr. Klein has since used in his textbook. So you're going to find it in several different places in your textbook. It's in the back of the chapter. It's also in one of the tables. But we separate all of our different 4 categories. Strong base, weak nucleophile. We're going to call that category 1. Strong base and strong nucleophile. We're going to call that category 2. A weak base but a strong nucleophile. We'll call that category 3. And a weak base and a weak nucleophile. We'll call that category 4. Once you determine what category the nucleophile/base fits into, then you can use the substrate to determine what kind of reaction it's going to be. It turns out that primary substrates prefer to do elimination reactions when we have situations of strong bases. Primaries then have one specific situation in which Sn2 reactions are going to predominate over E2 reactions, and that is when we have a strong nucleophile. So strong nucleophiles in primary substrates always do Sn2 reactions unless it starts becoming a strong base as well, and then it divvies up. However, it's still going to be mostly or primarily an Sn2 reaction for primary substrates. So the larger or the major product is going to be an Sn2. The minor product is going to be an Sn1. And that is for primary substrates when you have a category 2. If you have a category 1, it's going to predominantly give you an E2 elimination. If I go to secondary substrates and I still have a strong base, it's going to do E2. If I have a weak base and a strong nucleophile, it's going to do an Sn2. But what about in between? So now I have a strong base and a strong nucleophile, and I have a secondary substrate. Which is going to predominate? And this one is a little bit difficult. It's not exactly a 50-50 relationship, but it's pretty close. So you're going to end up having a mixture of both an Sn2 and an E2. If you have to choose between the two of them, I would say that E2 is going to be the major and Sn2 is going to be the minor. But on the test, I would always give both products as being the products of that reaction. I wouldn't risk it by just giving one of the two, because then I might get part of the question wrong. And in case that only one of them actually occurred, I would still get partial credit. So on a question for an exam, I would write down both. And then finally, if you have something that is a strong nucleophile but a weak base on a secondary substrate, it's going to do Sn2. Notice that if you have a weak base and a weak nucleophile, it's just not going to react with a primary or secondary substrate. There's just no incentive to do it. A weak nucleophile and a weak base, remember, that's water or ethanol. They tend not to react unless they absolutely have to. And the only way that they're going to do that is if there is a carbocation in place. So notice that you need, in order to do an Sn1 and an E1 reaction, you need a carbocation. And if we go back to looking at tertiary substrates are the only ones that do carbocations with any regularity, because anything else is too unstable. In fact, if you made secondary carbocation, it would very quickly rearrange to a tertiary carbocation before the nucleophile could actually react. So most of the time, unless you're tertiary or you rearrange to something that's tertiary, if you're creating a carbocation, you can only undergo Sn1 or E1 kind of reactions. And that's going to happen when you have a weak enough base or a weak enough nucleophile that can actually wait around for the reaction to have a leaving group leave to create the carbocation in the first place. In a tertiary substrate, you cannot and will not do an Sn2 reaction. Notice that none of these are Sn2 reactions, whereas the other ones do have Sn2s as part of what can happen with them. But with tertiaries, you cannot do Sn2 reactions. You can only do E2 reactions, which are preferred if you have a strong base. But if you don't have a strong base, then you're going to do a mixture of Sn1 or E1. All of these require the formation of a carbocation. In order to create that carbocation, you also have to have a really, really good leaving group. If you don't have a really, really good leaving group, you can't create the carbocation to begin with. So for the most part, these reactions just really suck. And that's not such a great word, but what it's trying to say is that those reactions are not really good reactions, and they lead to very poor percent recovery. They lead to reactions that give you many, many different products, and they're not reactions that scientists try to do. We try to do reactions that give us only one product. even those that have a mixture of products is not something we want to do, because then we'd have to separate the products before we could isolate it to get the product that we actually wanted. So we try to stay with the things that we know how to do and that we can do really well, so that we can produce the product that we want. So I hope this final video is going to help you to determine how to do these reactions. My recommendation is first to make little flashcards of all the 4 different types: nucleophile, strong base, weak nucleophile, weak base, and then to have and remake this chart over and over again until you feel comfortable with how to predict what the major product of a reaction is given this chart. So I hope that helps you put everything together. I'm going to make an introductory video for the next chapter, and then after that, all of the videos will be videos that have to do with specific addition reactions, which I'm going to borrow from reliable sources.